PharmaPal.
They have fewer hydrogens than the corresponding alkane would have, so they're unsaturated.
That's the term, yes, unsaturated. And the general formula for an alkene with just one double bond is CnH2n.
So ethene, C2, has 2 times 2, 4 hydrogens. C2H4 fits perfectly.
Yep, that double bond changes the formula in the chemistry.
Okay, next up, alkenes. Triple bond territory. Example, ethene, C2H2.
2 carbons again, but now only 2 hydrogens total.
So, following the pattern, how do they each get 4 bonds? Single bond isn't enough, double bond isn't enough.
They have to share 3 pairs of electrons. They form a carbon-carbon triple bond.
Wow. Okay, so each carbon has the triple bond to the other carbon, and then just one single bond to a hydrogen. 4 bonds total.
Correct. And like alkenes are unsaturated because of that multiple bond. Even more so, actually.
Makes sense. And the formula for one triple bond?
CnH2n2.
Ethene, C2. 2 times 2 minus 2 equals 2 hydrogens. C2H2. Checks out.
Perfect.
Now, the source mentioned something about bond strength and length.
Right. It's a bit counterintuitive, maybe, but the triple bond, while it's the strongest, takes the most energy to break.
Like snapping 3 pencils together versus 1.
Exactly like that. It's actually the shortest bond. Single bonds are the longest and weakest. Double bonds are intermediate in both strength and length, and triple bonds are shortest and strongest.
Okay, good distinction. So we've got the basic structures. Now, let's talk names. Common names and formulas for simple hydrocarbons.
Yeah.
This feels like where some pure memorization might come in.
There's definitely a bit of that, but there's logic too, especially with the prefixes. You really need to know the first 10.
Okay, list them out.
Methane is 1 carbon, CH4. Ethane, 2 carbons, C2H6. Propane, 3 carbons, C3H8. Butane, 4, C4H10.
Okay, meth, eth, prop.
Or
Those first 4 are a bit unique.
they are historical, yeah. But after that, it gets more systematic. Pentane is 5 carbons, C5H12. Hexane, 6, C6H14. Heptane, 7, C7H16.
Like geometry. Pent, hex, hept.
Exactly. Octane is 8, C8H18, think octopus. Nonan is 9, C9H20. And decane is 10, C10H22, like decade.
Pent, hex, hept, oct, non-decant. So those prefixes directly tell you the number of carbons. That's huge.
Absolutely crucial. Lock those down.
And for our simple alkene and alkene, we had ethene, C2H4, and ethene, C2H2, and there's propyne too.
C3H4, 3 carbons with a triple bond. And the alkene version would be propene C3H6, 3 carbons with a double bond.
Notice the endings. Ana for alkenes, N for alkenes, ethene for alkenes.
That suffix tells you the family. Non-negotiable.
Okay. Prefixes for carbon count, suffixes for bond type. Got it. Now, functional groups, those special atom groups, let's look at alcohols. Methanol, CH3OH is the example. How's that loose structure look?
Okay, start with the CH3 part that's a methyl group, carbon bonded to 3 hydrogens.
Right.
Now, instead of a 4th hydrogen, that carbon is bonded to an oxygen atom.
Okay, and oxygen.
Oxygen usually likes to form 2 bonds and has 2 lone pairs, those unshared electron pairs. So in methanol, the oxygen is also bonded to a hydrogen atom. That's its second bond. And it has those 2 lone pairs sitting on it.
And that alky-H group, the oxygen bonded to a hydrogen, attached to the carbon chain. That's the alcohol functional group.
That's your identifier, the eto-H group. And the name methanol comes from methane, the 1 carbon alkane. You drop the E and add ol.
Methane becomes methanol. So
Yep.
ol signals alcohol.
Exactly. Meth for 1 carbon, ol for alcohol.
Let's try a slightly bigger one, 2-propanol. CH3CH, CH3. The formula looks a bit condensed.
Yeah, the parentheses around the OH mean it's attached to the carbon right before it in the formula.
Okay, so prop means 3 carbons.
Right, a 3-carbon chain. The middle carbon, number 2, is bonded to a hydrogen and that OH group.
And the end carbons.
They each have 3 hydrogens, just like in propane. Everything still adds up. Carbons have 4 bonds, oxygen has 2 bonds and 2 lone pairs, hydrogens have 1 bond.
And the name, 2-propanol. Prop for 3 carbons, all for alcohol. Why the 2?
That tells you where the OH group is attached on the carbon chain. You number the chain, starting from the end that gives the carbon with the SOH group the lowest possible number.
Ah, okay, so in this case, it's on the second carbon, if it was on an end carbon.
It would be 1-propanol. The number is essential to distinguish between isomers like these.
Got it. Okay, moving on to ethers. Example, dimethyl ether, CH3OCH3.
The key feature here is that oxygen atom acting like a bridge between 2 carbon groups.
So a methyl group, CH3, then the oxygen, than another methyl group.
Exactly. And the oxygen has its usual 2 lone pairs. The common name is pretty descriptive. 2 methyl groups, so dimethyl ether. The di means 2 identical groups.
Makes sense. What if the groups are different, like ethyl methyl ether, CH3, CH2, CH3?
Okay, so you have an ethyl group, 2 carbons on one side of the oxygen, and a methyl group, 1 carbon on the other.
Right.
For common names with different alkyl groups, you just list them alphabetically, then add ether. So ethyl comes before methyl.
Ethyl methyl ether. Simple enough.
But IUPAC naming is a bit different for ethers.
How so?
It treats the smaller group attached to the oxygen as an alkoxy substituent on the longer carbon chain.
Alkoxy.
Yeah, like methyl attached to oxygen is methoxy, OCH3. Ethyl attached to oxygen is ethoxy, OCH2CH3.
Okay. So for CH3OCH2CH3, which is ethyl methyl ether in the common system,
the longer chain is the 2-carbon ethyl group. So the parent name is ethane. The OCH3 group is the methoxy substituent.
so methoxythane.
Precisely. Since it's on the first carbon of the ethane chain, it's technically 1-methoxythane, but often the 1 is dropped if it's unambiguous.
Okay, I see. And the other example, ethyl propyl ether. Common name's easy. Ethyl before propyl. IUPAC.
Longer chain is the 3-carbon protyl group, so the parent is propane. The substituent is the OCH2CH3 group.
Which is ethoxy.
Right. And it's attached to the first carbon of the propane chain, so it's 1-ethoxypropane.
Got it. And the source mentioned align structures briefly.
Yeah, just a shorthand drawing method. Lines represent bonds, ends and corners are carbons, hydrogens are implied. Saves a lot of time once you're comfortable with them. Definitely useful for exams.
Good tip. Okay, ketones next. What's their defining feature?
The carbonyl group, that's a carbon double bonded to an oxygen CO. And crucially, in a ketone, that CO group is located within the carbon chain, flanked by carbons on both sides, not at the end.
Okay, example, 2-butanone, CH3COC, CH2CH3.
But means 4 carbons. The CO is on the second carbon. Again, you number the chain to give the carbonyl carbon the lowest possible number.
And the ending.
The suffix for ketones is 1. So butane becomes butanone. And the 2 tells you where that carbonyl group is. 2-butanone.
The source says the number can sometimes be omitted if it's obvious, like for butanone.
Yeah, because if you put the CO on the third carbon, numbering from the other end makes it carbon 2 anyway. There's only one place for it, effectively. But for longer chains, like 3-heptanone...
And hept is 7 carbons. 1 means ketone. 3 means the CO is on the third carbon.
Exactly. You need the number there, because it could also be 2-heptanone or 4-heptanone.
Okay. So what if that carbonyl group is at the end of the chain?
Then it's not a ketone, it's an aldehyde. That's the key difference.
Aldehydes. The source flags the -CHO group.
Right. That means the carbonyl carbon, COO, is also bonded to at least one hydrogen atom. This forces it to be at the end of a carbon chain.
Example, ethanol, CH3CHO.
Eth is 2 carbons. The suffix for aldehydes is -yle. So ethane becomes ethanol.
Do we need a number?
Nope, because the aldehyde group, CHO, is always at the end. It's always considered carbon number 1. No number needed.
So pentanol would be?
I have 5-carbon chain, with the DOCA-CHO group at the end. Pentane becomes pentanol.
Ketone CO is internal, aldehyde CO is terminal. Got it. Next, carboxylic acids. They have NTHOH or NetCO2H.
Yeah, that group combines a carbonyl CO and a hydroxyl attena on the same carbon atom.
Okay. Example, propanoic acid, CH3CH2COH.
Prop means 3 carbons total. The carbon in the ETOH group is always carbon number 1.
And the naming.
You take the alkane name, propane, drop the E, and add aoic acid. So propanoric acid.
And like aldehydes, no number needed because the NeCOH is always at carbon 1.
Correct. So octanoic acid is just an 8-carbon chain with a diCOH group at the end. Octane becomes octanoic acid.
Okay, now esters. RKHO looks like a carboxylic acid derivative somehow.
Exactly. Think of it as a carboxylic acid reacting with an alcohol and losing a water molecule. The ADOH from the acid is replaced by an HOR from the alcohol.
The example is methyl ethanoate, CH3COCH3. How do we name that?
It's a 2-part name. First, you name the alkyl group that came from the alcohol part, the part attached to the single bonded oxygen. In this case, it's the negative CH3 group on the right.
So methyl.
Right. Then you name the part that came from the carboxylic acid, changing the icoic acid ending to oat. The CH3CO part comes from ethanoic acid.
So ethanoate.
Put it together. The alcohol part first, then the acid part. Methyl ethanoate.
Okay, alcohol part, alkyl name, plus acid part, oat name. Got it. Amines next, RNH2. Nitrogen's involved.
Yep, amines feature a nitrogen atom bonded to 1 or more carbon groups. And nitrogen usually has a lone pair of electrons. Simplest is RNH2, a primary amine.
Example, ethylamine, CH3CH2NH2. Common name seems straightforward.
Yeah, ethyl group attached to the amino group, NH2, so ethylamine.
IUPAC.
You can treat the anika NH2 as a substituent called amino, so ethylamine could also be called aminoethane.
And if it's on a longer chain, like 2-aminopentane.
That means you have a 5-carbon chain, pentane, and the amino group NAC-NH2 is attached to the second carbon. The number indicates the position, just like with alcohols or ketones.
Okay, and amides. They look similar, but have that CO next to the nitrogen, RCONH2.
That carbonyl group makes a huge difference chemically. The example is butanamide, CH3CH2CH2CONH2.
But for 4 carbons.
Right. You take the alkane name, butane, drop the E, and add a minus, butanamide.
Okay. The source also briefly mentions nitriles, C triple bond N, acid chlorides, COCl, and benzene rings, C6H6 aromatic.
Yeah, just a heads up that there are more functional groups out there you'll encounter later. Benzene rings are particularly important in aromatic chemistry.
Definitely more to learn, but this covers a lot of the core ones. Okay, let's shift gears to formal chart. Why do we need this?
It's basically electron bookkeeping. It helps us see how electrons are distributed in a Lewis structure, identifying atoms that might be electron-rich or electron-poor, which often relates to reactivity.
And the formula.
Formal charge, valence electrons of the neutral atom, number of bonds the atom is forming, number of lone pair electrons around the atom.
Okay. Example 1. Oxygen with 1 bond and 3 lone pairs. 6 non-bonding electrons. Oxygen starts with
6 valence electrons.
So 6 minus 1 bond minus 6 lone pair electrons equals -1.
Correct. That oxygen carries a negative formal charge, common in alkoxide ions.
Example 2. Oxygen with 3 bonds and 1 lone pair. 2 non-bonding electrons, like in protonated alcohol.
Still starts with 6 valence electrons, so 6 minus 3 bonds minus 2 lone pair electrons.
Equals +1. A positive formal charge.
Right. Makes that oxygen electron deficient and more reactive.
Example 3. Nitrogen with 2 bonds and 2 lone pairs. 4 non-bonding electrons. Nitrogen starts with
5 valence electrons.
Okay. 5 minus 2 bonds minus 4 lone pair electrons equals -1.
Yep. Yeah. A negative formal charge on the nitrogen. So calculating formal charges helps assess the quality of a Lewis structure and predict potential reactivity.
Very useful. Now, related to Lewis structures is resonance. What's that about?
Sometimes a single Lewis structure just doesn't accurately represent a molecule or ion. The actual electron distribution is a blend or hybrid of multiple possible Lewis structures. These different structures are called resonance structures.
And only electrons move, right?
Yep.
Not the atoms themselves.
Absolutely. Key point. Atoms stay put. Only pi electrons and lone pair electrons typically shift around. We show this movement using curved arrows. A full arrow for 2 electrons, a half arrow, fishhook for 1, though we mostly use full arrows here.
Okay, example. The ethanoate ion,
And acetate.
CH3COO.
Right. You can draw one structure with the double bond to one oxygen and the negative charge on the other oxygen, which has 3 lone pairs.
And the resonance structure.
You use curved arrows. Take a lone pair from the negatively charged oxygen, move it to form a double bond between it and the carbon. Simultaneously, the electrons in the existing CO double bond move onto the other oxygen as a lone pair.
So the double bond shifts and the negative charge shifts to the other oxygen.
Exactly. And you draw a double-headed arrow between these 2 structures to show they are resonance contributors to the actual molecule.
In this case, the 2 structures look identical, just mirrored.
They are equivalent. This means the negative charge isn't really sitting on just one oxygen, it's delocalized, spread equally over both oxygen atoms. This spreading out stabilizes the ion.
Ah, stabilization through delocalization. Okay.
Yeah.
What about the amide example?
In an amide, RCONH2, you have the main structure with the CO double bond. But the nitrogen next door has a lone pair.
Can that move?
Yes, that lone pair can move to form a double bond between the nitrogen and the carbonyl carbon. At the same time, the CO pi electrons move up onto the oxygen.
So now you have a CN double bond, a CO single bond, a positive charge on nitrogen, and a negative charge on oxygen.
Correct. That's a second resonance structure. But these 2 aren't equivalent.
Why not?
The first structure, with no formal charges, is generally more stable. The second one has charge separation plus on N, on O, which is usually less favorable. So we call the first structure the major resonance contributor, and the second one the minor contributor.
So the real molecule Looks mostly like the major structure, but with some character of the minor one.
That's the idea. Resonance explains why the CN bond in amides has some double bond character and is harder to rotate around than a typical CN single bond.
Interesting. The source also showed allylic anions and chemations.
Yeah, similar idea. If you have a charge, positive or negative, or a lone pair on a carbon next to a double bond, the allylic position, you can draw resonance structures by shifting the double bond and moving the charge or lone pair. Again, it delocalizes the charge, which leads to stabilization.
So resonance is all about showing electron delocalization, which often leads to increased stability.
That's the core concept. It's a way to better represent molecules where electrons aren't strictly localized between two atoms or on a single atom.
Okay, great. Finally, let's circle back to IUPAC naming. But for more complex alkanes with branches, substituents, what are the rules?
There's a system. Rule 1. Find the longest continuous chain of carbon atoms, that's your parent chain, and you name it based on the number of carbons, hexane, heptane, etc.
Longest continuous chain. Got it.
Rule 2. Identify any groups attached to that main chain that aren't part of it. These are your substituents. Name them, e.g. methyl for mean it to CH3, ethyl for net it to CH2, CH3.
Okay, find the parent, find the branches.
Rule 3. Number the carbons in the parent chain. Start from the end that gives the substituents the lowest possible numbers, or locants.
Lowest numbers rule. Crucial.
Very. Rule 4. Assemble the name. List substituents alphabetically, ignoring prefixes like D, tri, unless they're part of the substituent name itself, like isopropyl. Use numbers to show where each substituent is attached. If you have multiple identical substituents, use prefixes like tri, tetra.
Okay, let's try an example. 3-methylhexane.
Longest chain is 6 carbons hexane. There's a methyl group next CH3 attached. Numbering from the correct end puts it on carbon 3, so 3-methylhexane.
Makes sense. Example 2. 3-phenol-4-dimethylheptane.
Longest chain, 7 carbons heptane, substituents, 2 methyl groups.
Okay, dimethyl.
Now numbering. We need the lowest numbers. If we number from one end, they're on carbons 3 and 4. From the other end, they'd be on 4 and 5. So 3 and 4 are lower.
Right. So 3-phenol-4-dimethylheptane.
Perfect. You need a number for each substituent, even if it's the same number repeated for di or tri.
Last one, 5-ethyl-4-methyloctane. That's more complex.
Parent chain. 8 carbons octane. Substituents, an ethyl group and a methyl group.
Okay, ethyl and methyl. Now alphabetizing and numbering.
Alphabetically, ethyl comes before methyl, so we list ethyl first in the name. Now, numbering the octane chain. We want to give the first alphabetical substituent, ethyl, the lowest possible number if there's a choice, or ensure the set of numbers is the lowest overall.
So numbering from one end might give 4-ethyl and 5-methyl. Numbering from the other gives 5-ethyl and 4-methyl. Which set is lower?
We compare the sets, 4, 5 versus 5, 4. At the first point of difference, 4 is lower than 5. Wait, let me rephrase that based on the source. The rule is often stated as lowest number at the first point of difference. Let's recheck 5-ethyl-4-methyloctane. If we number from the left, methyl is 4, ethyl is 5. If we number from the right, ethyl is 4, methyl is 5.
Okay, so 4, 4, 5, starting from the right gives ethyl the lower number 4. But wait, the example name given was 5-ethyl-4-methyloctane. Why?
Good catch. Let's reread that complex rule part. Sometimes it's lowest number for the substituent cited first alphabetically if the sets are otherwise equivalent upon first difference. Let me rethink. Octane chain. Substituents at C4 and C5. One is methyl, one is ethyl. Numbering from left, C4 methyl, C5 ethyl. Numbering from right, C4 ethyl, C5 methyl. The sets of numbers are 4, 5 either way.
Okay, so the numbers themselves don't decide it here.
Right. When the numbering gives the same set of locants, the substituent that comes first alphabetically gets the lower number. Ethyl comes before methyl.
So ethyl should get the 4, meaning numbering from the right, which would make it 4-ethyl-5-methyloctane. The source example says 5-ethyl-4-methyloctane. Let me double check the original notes.
Yes, double check that specific example's logic. IUPAC rules can have tiebreakers. Okay, looking back at the provided context, the example given is 5-ethyl-4-methyloctane, and the rationale mentioned prioritizes the lowest number for the first substituent listed alphabetically when choosing between numbering schemes if sets are otherwise tied. Wait, perhaps the rationale explanation itself in the notes was slightly off, or my interpretation. Let's assume the name 5-ethyl-4-methyloctane is correct as given in the source material. It implies numbering from the end that gives the methyl group C4 and the ethyl group C5. Why? Perhaps the lowest number overall principle is being applied in a way that considers the sum, or maybe prioritizing the simpler substituent. No, the standard rule IS lowest number at first point of difference then alphabet priority for the lower number.
Okay, this specific example might need careful re-examination against strict IUPAC rules, but the general principles are: find longest chain, identify substituents, number for lowest locants, list alphabetically. That's the core takeaway for exam prep.
Agreed. Focus on those core rules. They'll handle the vast majority of cases you'll see. Master finding the parent chain and applying the lowest number rule consistently.
PharmaPal.